All right, welcome back. What you're going to find in the second part, the spreadsheet makes things fairly linear for us. There's not many deviations here. All we need to do is learn about a small change in our spreadsheet when we're working with the data. Okay, so first example. For the given data on bacterial growth, we want to answer the following. So we want to create a scatter plot. That doesn't change how you do that. Determine the type of regression curve. So that takes a little bit of thought, but the spreadsheet is so nice because it allows you to flip through and pick the best possible option. All right. So if you open up lesson 19, if you want to work along with me, the data is already entered. So it's all plotted or all typed in there. So again, you select the data, insert, chart, more, scatter, scatter, customize. All right. So inside the customize one, we are doing, you know, population versus time. Horizontal axes here. So on the horizontal, we will have time in hours. And we want to go from 0 to 10 sounds good to me. On the vertical, we've got population. And I want to go from, say, 0 to the 600 is fine. That's there. So right away, at this point, you can take a quick peek here. You can see this is definitely not linear. So the question then becomes, what type of graph is it? So I'll just kind of answer this on as I go. So A, C graph. B, determine the type of regression curve that we're going to use here. So this will come with experience. You'll get quicker at it. But if you're not sure, you go trend line and you try linear and you go, that doesn't look very good. Okay, it's obviously a curve. Well, you have several curves that you can follow. Okay, now as I mentioned in the first video there, r squared is now, if we're going to go to nonlinear, we're using r squared. So what other choices do we have? So we look at our trend line. We have exponential, and that is pretty impressive on exponential, 0.995. However, you do have other options. You can pick polynomials, as mentioned before, and you can just change the degree in here. So 3, 4, 5. Now here's where you got to be a little bit careful with polynomials. Polynomials like to fit given points. So I now have an R value of 1. But my question to you was, or my question is, it says the initial value was 100 and the population dropped. Okay, so this is where we got to use a little bit of common sense. If we go back to the original data, we see that 1 hour there's 10, 2, 21, 3, 43. This is going to continue to grow. Okay, this is a growth model. So at this point in time, there's no indication the bacteria will stop growing. This graph choice shows that all the population is going to die in about 9 hours. Is that the case? I don't think so, because we're looking at the population increasing all the way through. So that's why I would say be careful with which ones you pick. You have to use common sense, and you will be graded on that common sense. So you got to assume, I can't have my population start high. So I'm going to go back down. Okay, 4, I'm still having a population drop, so it's not good. 3, it's not bad, but here's my problem with the degree 3 polynomial. If you look at it, the population decreased before increasing. Okay, that area can't happen. I go to a parabola, a quadratic, and same problem. So really, although the exponential has a lower r squared value, it suits the situation, or it models the situation best, because it continually increases and it decreases down to 0, 0. All right, so those are some of the factors I will be expecting you to be aware of. So determine the regression curve. I decided it must be exponential because it is the only model that shows continued growth after the last data point and did not have a decrease in population prior to my first point. Okay, so very, very important that you can go through and tell me the best model and the one that makes the most sense. How did you know your choice? So I'm going to put B and C together here because I kind of answered them in one shot there. Okay. Um, it also had a very high correlation factor, so positive correlation factor. All right, and that was 0.96. All right, so D, determine the equation. So again, this is why I would recommend if you, and this is what I just want to show you, if you put the equation in, you see how you can't see it on the right side here? So if you leave it long enough that you can put the cursor on this curve, you can see the equation you want. Now, this is kind of interesting because they use a factor of E on the calculator, and that's not a big deal. So my actual equation is let's call it 5.7. So so D part, y equals 5.7 e to the exponent, all right, what was it then, to the exponent 0.66x. So with an exponential function, we would write it out like that, and I will tell you right now that e is approximately equal to 2.71, and there's an E button on your calculator. If you pull up your or look at your calculator, there is an E button there. All right, I'm just going to slip to the board to write that out in a little better form. So y equals 5.7 e to the exponent 0.66x. And e is just a special function. Okay, so e is what we call a natural base. You don't really need to have that memorized or anything. You just need to know that either use the E button on your calculator or E is about equal to that 2.71 value. Okay? Either way, it doesn't matter to me which way you do it. It's the value that the spreadsheet spits out, and I'm not going to bother spending time learning how to convert it. We'll just use that base E. Okay? So then the next part is making a prediction with the model that you came up with. So we are going to answer right on the page here. So E, we're going to let X equal 24. And up here I should have said let Y represent population. Let X represent time. I know I'm getting tisk to be sure. So y equals 5.7 e to the exponent 0.66 times 24. So if you want to pull out your calculator, just to make sure that you know how to use the calculator in that button, you should get approximately the following: 4,300,000, oops, I'm out of factor there. I think that's 43,161,791 bacteria. So moral of the story here, don't leave dirty dishes under your bed for a long time because bacteria grows exponentially. So, all right. So there's that example taken care of. And let's move along to the next one. The next one, very similar in the sense that it's using the same process. So the following is information taken from a lab. I actually took this from a physics lab. And it's going through the same process. So if we go back here, insert, we're going to go to the next slide. Example number 2. There's my data. I'll go through this one a little bit quicker since I've done all my talking already. Scatter, scatter, customize, and this is a distance versus time graph. So if anyone's taken Physics, you'll recognize the dt graph. Horizontal is my time, but it's already 0, 0, which is great. Vertical is distance. That's in meters. So moving down, we're interested in that trend line, so you go through and you decide, it's definitely not linear. Now I look at my exponential, and I'm going to put that R value on. 92% or 0.927. It's not bad, but it seems to be a little more steep or extreme. So I'm going to go to, polynomial, and we'll start at degree 2, and that's bang on, that's 1. All right, I mean, you can try some of the other ones, but you might as well stick with the lowest degree. Okay, so there's your polynomial. So if I pull this up and answer some of the questions here officially, A, C graph, B appears to be quadratic or polynomial degree 2. Explain my decision. The quadratic provided a perfect correlation factor and appeared to fit the data best. All right. D, your equation. And like I said before, don't hit insert until you get your equation, because again, if you label it using equation, it's tough sometimes to get the information. Now that's not too bad, but I'm going to just pull it off of here. So it looks like 4.91x squared. So y equals 4.91x. I don't have a subscript button, so x squared. Then what happened? Plus 1.279 to the exponent negative 13. Negative 13, that's a very small number. Okay? That's like 1.29, but that's with 12 zeros ahead of the 1. So that's essentially a 0. And the same with the last number. So that exponential notation where it says e negative 13, e to the negative 13 is essentially 0. And probably I would say if you run into e to the exponent negative 5 or bigger, that we're going to assume it to be 0. So we're going to leave that as the equation right there, 4.91x squared, where, not going to get caught this time, y represents distance and x represents the time. So people that have taken physics, this is because this is just your y equals 1/2 at squared formula. V1 is 0. For those that didn't take physics, you don't have to worry about it at all. All right. E, determine the distance after 5 seconds based on my information. I don't know why I'd pick 5 seconds. Oh, I know why. Because it is in my chart. That's what I was thinking originally. But I want to see how close that model is. So if we let x equal 5 seconds, y equals 4.91 times 5 squared. So again, that formula, because I don't have that superscript button, that's what that formula is. So punching that into the calculator, we get 4.91 times 25. We get 122.75 meters. And if we take a look up here at 5 seconds, it's pretty close. All right. So that gives you an idea of how to handle the nonlinear. Take the homework questions off the website. Ignore the video because those have been adjusted. But there you go. So it's just an extension of what we've been doing already. So good luck, and we'll see you tomorrow.